The Arabian Peninsula sits on almost no permanent rivers, no natural lakes, no mountain snowmelt to feed a thirsty population. What it does have is 3,000 kilometers of coastline and an ocean of salt water that no human being can drink. So Saudi Arabia did something no nation had attempted at this scale. It decided to move the sea inland. Along the Red Sea coast, intake stations the size of small factories began pulling in seawater by the billions of liters, pushing it through pressurized steel pipelines that stretch for hundreds of kilometers across open desert. Enough. Water moves through these lines every single hour to fill more than 4,000 Olympic swimming pools. The pipelines climb elevation changes that should be impossible for water this heavy, this corrosive, this unforgiving on metal. Engineers called it a triumph of modern infrastructure. A kingdom built on sand would drink from the ocean. But somewhere between the coast and the capital, something in the system began to fail. Not all at once. Quietly, in the joints and valves, no one was watching closely enough. What started as routine pressure monitoring would soon reveal a flaw buried inside the very success of the project. One that would force engineers to confront a question they hadn't planned for. What happens when you ask the desert to hold an ocean? It was never built to carry. Riyadh was never supposed to become a city of 7 million people. Not in a place where annual rainfall barely covers a few centimeters. Not in a place where the water table had been dropping for decades. By the 1970s, engineers already knew the fossil aquifers beneath the kingdom were running dry. Ancient water, trapped underground for thousands of years, was being pumped out far faster than nature could ever replace it. Officials called it a slow-motion emergency. Farms were draining reserves meant to last generations. Cities were expanding into land with no reliable water source at all. Something had to give. The first proposals sounded almost absurd. Build pipelines from the coast to the interior. Push desalinated seawater uphill across hundreds of kilometers of open desert, using pressure alone to fight gravity and distance. Critics inside the ministry called it reckless. The terrain climbed nearly 1,000 meters in elevation. No pipeline network on this scale had ever been built through terrain this brutal, this remote, this unforgiving on equipment. But the alternative was worse. Do nothing, and the capital would eventually run dry. In 1980, the government approved the plan anyway. Construction crews broke ground along the Red Sea coast, laying the first sections of pipe under a sun that regularly pushed past 45 degrees Celsius. Steel pipes wide enough for a grown man to crawl through were lowered into trenches cut straight through solid rock. Engineers on site described the project as a race against physics itself. What none of them fully understood yet was that the desert wasn't just an obstacle to cross. It was about to become part of the problem. The pipeline crews worked in, shifts around the clock, chasing the cool hours before dawn. Even then, surface temperatures on. The exposed steel climbed hot enough to blister a bare hand in seconds. Every section of pipe had to be welded, pressure tested, and buried before shifting desert sands could bury the equipment. First, convoys hauled materials for hundreds of kilometers along routes that barely qualified as roads. Some trucks broke down and were simply abandoned where they stalled, swallowed by dunes within weeks. At the coastal stations, desalination plants ran non-stop, stripping salt from seawater on an industrial scale. No one in the region had attempted before. The numbers alone were staggering. Enough treated water to supply a major city, pushed uphill through pipe wide enough to walk through standing upright. Pumping stations were spaced every few dozen kilometers, each one fighting gravity, friction, and distance, just to keep the water moving forward. Engineers on site started noticing something strange in the early data. Pressure readings that should have stayed constant were fluctuating in patterns nobody could immediately explain. At first, supervisors dismissed it as instrument error. Desert heat could distort even the most reliable sensors. But the fluctuations kept returning, always in the same sections, always after the pipeline had been running longest. One field engineer later admitted the readings gave him a feeling he couldn't shake. like the system itself was trying to tell them something they weren't ready to hear. By the time the first full stretch of pipeline reached operational capacity, the celebrations barely lasted a week, because deep inside the buried steel, something was already changing, and nobody yet understood what they had actually built. The answer came from a maintenance crew doing routine inspection work. They cracked open an access valve nearly 200 kilometers inland, expecting the usual buildup of mineral scale. What they found instead made no immediate sense. Salt crystals, thick and jagged, had formed along the interior walls of the pipe, far beyond anything the desalination process should have allowed through. A senior engineer ran the numbers twice before he believed them. Trace amounts of salt, invisible at the coast, were slowly concentrating over hundreds of kilometers of travel. Evaporation at pumping stations was making the problem worse with every cycle. It was a slow chemical. Betrayal, hidden inside a system everyone had trusted. Left unchecked, the crystallization would narrow the pipeline's interior, choke water flow, and eventually crack welds under rising internal pressure. Word spread through the project quickly. Engineers who had celebrated months earlier now spoke in clipped, worried tones during inspection briefings. One supervisor reportedly stood in front of the exposed valve for nearly a full minute without saying anything at all. Then came the second discovery, the one nobody wanted to say out loud. The corrosion wasn't uniform. It was worse in sections that ran closest to shallow desert aquifers, as if something underground was reacting to the pipeline itself. Soil samples were rushed to a laboratory in Riyadh. The results, when they came back 3 days later, would force project leadership into an emergency meeting that lasted until well past midnight. Because the salt wasn't just damaging the pipes, it was beginning to move somewhere else entirely, somewhere far more difficult to control. The lab results confirmed what no one wanted to hear. Trace salt from minor leaks along aging pipe. Joints had been seeping into the shallow soil for months, maybe longer, and it was migrating toward the very aquifers the pipeline was supposed to protect. For a project built to solve a water crisis, the idea that it might be poisoning groundwater instead felt almost unbearable. Project leadership scrambled to contain the damage before it reached local wells still used by desert communities. Emergency crews were pulled from other sections and redirected to the affected stretch within 48 hours. Excavators tore into the desert floor, exposing pipe joints that had been buried for less than 2 years and already showed signs of stress corrosion. One engineer described the exposed metal as looking decades older than it should have. The kingdom's oppressive heat cycles, scorching days, cooling nights, were expanding and contracting the steel far more aggressively than early models had predicted. Every contraction opened microscopic gaps. Every gap let a little more salt escape. Repair teams worked in 12-hour shifts under floodlights, racing to reinforce joints before the next seasonal heat wave arrived. Then, during one overnight inspection, a supervisor noticed something that stopped the entire operation cold. A section of pipe near a known fault line in the earth had shifted position by nearly 4 centimeters. Nobody could explain how or when. Reports were sent immediately to Riyadh, flagged as urgent. Because if the ground itself was moving, beneath the pipeline, the salt leaks were no longer the biggest danger. Something far more destructive was now in play. And the desert wasn't finished testing what they had built. Geologists arrived within days, working alongside the engineering team to map the shifted section meter by meter. What they found offered a strange kind of relief. The movement wasn't seismic, it was subsidence. The ground settling as decades of groundwater extraction quietly hollowed out pockets beneath the desert floor. Still dangerous, still unpredictable, but not the catastrophic fault rupture some had feared in those tense overnight hours. Engineers redesigned the vulnerable sections with flexible joint couplings, allowing pipe segments to shift slightly without cracking under stress. Corroded stretches were replaced with corrosion-resistant alloys, refined specifically for the mineral content found in the leaked samples. Monitoring stations, once spaced for efficiency, were multiplied along the highest risk corridors. sensors now checking pressure, and soil chemistry in real time, not weeks after the fact. It took nearly 2 years of continuous repair work before officials considered the system stable. Today, that same pipeline network moves billions of liters of desalinated water across the kingdom every single day, supplying cities that would otherwise have no reliable source at all. But the scars of that early crisis never fully disappeared. Engineers who worked the original project still describe those months as a lesson etched permanently into the industry's memory. Proof that moving an ocean inland comes with a price the blueprints never mentioned. The desert didn't defeat the pipeline, but it forced an entire nation to rebuild its relationship with the water running beneath its own sand. Some victories over nature, it turns out, are never really final. If stories like this one keep you thinking long after they end, you already know what to do next.